CMA-ES and Bayesian Optimisation.
Yeah, thank you, Josh. Hi, everybody. So yeah, I am Léni Goff. I'm currently a postdoctoral research fellow at the Edinburgh Napier University, and I will present you some output of the Autonomous Robot Evolution project. So the goal of the ARI project is to evolve both the morphology and the behavior of robots, and also to evolve them jointly in simulation and in reality. The robots which are worth it are printed and assembled thanks to a robot fab, and they could be tested, evaluated in reality as well as in simulation. So in terms of learning a controller, this project raises some interesting challenge of number of two. So I will speak about two of them. We have no prior knowledge about the shape of the robot, whether it's dynamic or its morphology. And the second one is the reality gap, of course, which is a very common and important issue in evolutionary robotics. To tackle these challenges, we choose to explore machine learning method which can converge to satisfactory solutions, satisfactory controller very quickly. Quickly in terms of number of samples, samples is equivalent to an evaluations in evolutionary robotics. So how much time you put your robot in the arena and you evaluate it on compute its fitness, and also quick in terms of time, the computational time needed to reach a satisfactory solution. If you have a machine learning method which is sample efficient and time efficient, you can apply it a large amount of time, which means that, for example, you could learn from scratch each time a controller for each new morphology. Also, you can apply it directly in reality because you don't have to do a lot of evaluation, which is costly in reality with robots. So you can bypass in this way the reality gap problem. So there is many works in the literature, of course, that tackle this problem of learning quickly, and specifically the problem of sample efficiency in reinforcement learning and also in policy search in robotics. Interesting survey, recent survey and policy search algorithm for learning robot controllers in a handful of trials, in which in their conclusions they outline two methods called black drops and Pilco, which have very impressive results for the task. You can see the picture here, like gait learning for hexapod, learning the inverse kinematic of an arm robot, or the classic cart pull task in reality. They are able to solve this task in between 10 or 50 evaluation, which is quite impressive. These both methods are based on Bayesian optimization, and also they learn a model of the dynamics based on Gaussian processes. The main issue with this method is they are very heavy in terms of computational time. If you have a problem, and this is what they say also in their conclusion, if you have a problem with a large state space, this method could take hours or days to process just a few trials. To overcome this issue, they choose to, for example, they propose to use priors on the dynamics of the robots, which is something we cannot afford in the ARI project, as we have no prior knowledge about the body plan of the robot. Another interesting work which tackles this problem of the computational complexity of Bayesian optimization, called BEA, show very clearly this issue. Bayesian optimization have a cubic complexity in number of samples, and also an exponential complexity in size of the parameter space. You can see on the graph on the left part of this slide, the same results comparing on the same task, the objective over the number of evaluation for EA and BO, and over the time. Over the evaluation, you can see that clearly Bayesian optimization is better than EA, but this is not that clear over the time. EA is could be still a good choice. So they propose a method in which they bootstrap an EA with the dataset of a Bayesian optimization, because Bayesian optimization is still time efficient at the early iteration of the learning phase. And they tested this on a gate learning with modular robot. All the work I talked to you about just now they all tested their method on the same kind of problem, gate learning, learning AKI for arm robots. And in this kind of problem, the robots are quite complex and all the difficulties inside the configuration of the robot. Here, in this work, we want to find a sample efficient, time efficient method for navigation task in which the major difficulty is in the environment. The kind of difficulty you can face is, for example, deceptive rewards, which is equivalent to local optima in optimization problem, in which the robot can be stuck on a wall near the target, but not being on the target yet. A good approach to overcome this difficulty is to use evolutionary algorithm, because this is population based, so we have higher exploration power than reinforcement learning or Bayesian optimization. And you can even add novelty search, which put additional selection pressure toward novel individuals and toward exploration. So here we propose two methods. One called NIPES, which is based on the classical IPOP CMA-ES, so increasing population size. CMA-ES, so I won't go into the details because of the time constraints, but the main idea here is to start from small population, here in our case 10 individuals in the population, and increase it if it is needed. To know when it is needed to increase the population, we have stopping criteria, and we propose here two stopping criteria. The first one is if the standard deviation of the population's fitness is under a certain threshold, which means that all the individuals are performing in the same way, which means that probably the solution are stuck in a local optima. The second one is the standard deviation of the best fitnesses over a certain amount of generation is under a certain threshold, which means that you don't improve anymore your policy. So in this case, you restart and increase your population, you multiply it by 2. Also here, we propose an objective function, which is a linear combination of novelty and reward. The second method is NBOES, which is directly, we draw directly inspiration into the BEA work. So as in BEA, we bootstrap a CMA-ES method with a dataset produced by a Bayesian optimization. We run Bayesian optimization for a certain number of iterations. So here the objective function of the Bayesian optimization is just the reward, and the objective function of CMA-ES is, as before, the novelty plus reward, the linear combination. So the idea here is to let CMA-ES starting from a good point, good starting point, instead of starting directly with a random starting point. So to compare these two methods, we have conducted an experiment on 3 different arenas: the escape room, middle wall, multi-maze, and easy race, which are increasing in terms of difficulty. The easiest one is the escape room, and the most difficult one is the easy race. And we have tested it with 2 robots, the airy puck and the airy potato. So airy puck is designed to be well fitted for the navigation, where airy potato is less fitted for navigation. To complete the task, the robot have to reach the target within 5% of accuracy, which is shown by the right circle on the pictures of the mazes, and have a budget of 10,000 evaluations or samples. If one robot during one generation is able to complete the task, we stop the evolution. So we have conducted 3 series of experiments: decomposition of NIPES, in which we compare CMA-ES alone, then CMA-ES plus novelty, and then the full package NIPES, so restart plus novelty, and also decomposition of NBOES, in which we compare Bayesian optimization alone and novelty with CMA-ES and NBOES, and the final game in which we compare NIPES and NBOES. So to the performance measure will be the sample efficiency and the time efficiency, so the number of samples needed to complete the task and the computational time, total computational time needed to complete the task. So as first result, the decomposition of NIPES. So here, Novelty seems to reduce the number of samples needed apart from the multi-maze, which tend to indicate that this is dependent of the novelty is dependent of the environment, sorry, which is expected because if there is no deceptive reward, for example, in the environment, there is no interest into the novelty. And the restart, as expected, reduce the number of samples, which is clearly shown on the multi-maze and easy race. Be aware that the y-axis on the graph are log scale. Then the decomposition of NB-ES. So here you have on the left the best reward shown, and on the right the computational time. Here we being able to run only with 300 samples of budget because of the computational weight of BO. After this, that the experiment was taking too much time. As the numbers above the boxes on the best reward graph shows the number of replications able to complete the task within the 300 sample of budget. So this is not very significant. We don't see significant difference in terms of performance, but in terms of computational time, this is quite significant. The NB-ES improves significantly the time efficiency, and the best one is CMA-ES. So the final game. So here we have on the left the number of samples. Again, you have the number under and above the boxes, which indicate the number of replications that was able to complete the task. And on the right, the computational time needed to complete the task. Again, the y-axis are in log scale. So here, this is not very clear which method is the best in terms of sample efficiency. Sometimes this is NB-ES for certain environment, and other time is NIPES, but this is quite clear in terms of computational times that NIPES is better than NB-ES. Also, some interesting side results. As expected, the algorithm need more samples to find a good solution for the hairy potatoes and the hairy puck, and the most complex environment, as expected, is the easy race. So to conclude, there is no best candidate in terms of sample efficiency. However, NIPES, by having a good sample efficiency, is better than NB-ES in terms of time efficiency. So NIPES is a promising method, but we still need to test it on other task domain or also on more complex task and in reality also. Also, Bayesian optimization seems not to fit to the problem we try to tackle here. First, because the parameter space size is of 168, which is quite big. Because we use a recurrent neural networks, for example, to compare in the BEA paper, the biggest parameter size is of 18, which is smaller. And also the second thing is maybe our robot is too simple. This is just real robot, and the potential of Bayesian optimization could be unveiled only with complex dynamics robots, maybe because all the literature use Bayesian optimization with complex robots and so on. So I would like to thank all the team of the ARI project. We are doing very fun work, and thank you for your attention. Feel free to ask any question.
Thank you, Léni.
Thank you.
I think Jan has a comment, and then Andy is asking for a clarification. So Jan, did you want to ask your or suggest your comment?
Shall I ask my question?
Yes, go for it, Andy. Go for it, Andy.
Léni.
Yeah.
Yeah.
The CMA-ES was the best result overall, was it?
Yes, CMA-ES with novelty on the restart. with increasing population.
Because the I think the on the second slide of the results,
Yeah.
I think the green is the CMA-ES because it's
Yeah.
MBO. Okay, okay. And so did you try that on the? You didn't try CMA-ES on the final results for the
No.
potato? No.
No, but I have compared NIPES with the CMA-ES with Novelty. So you
Yep.
can see on the first slide with NIPES, and also I have compared it with NBOES. So we can see that the restart improve in terms of sample efficiency quite significantly the results, because you start from a smaller population. So mainly that improves the sample efficiency, because if you reach a first good solution with small population, you did less evaluation.
And so do you think if you did so if you just did some local hill climbing or something at the beginning to get into a good region of space, would that have the same effect in sort of increasing efficiency?
This is an interesting suggestion. I think this is the idea of bootstrapping CMA-ES with Bayesian optimization, because Bayesian optimization is very exploitative method, and we try to find like the best starting point at the beginning. We run it in NBOES, we run it for 50 iteration first. So we have a first population of 50 solutions, which normally have been optimized by the Bayesian optimization process.
Okay, thank you.
Yeah, thank you for your question.
Okay, thank you again. Our